Thank you very much for attending this webinar, this seminar on meta-analysis. Today, my colleagues, George Kapetanios, who is my co-director at the DAFM Research Center, and Jack Fosten, who is the deputy director, we are delighted to have with us Professor Tom Stanley. Professor Tom Stanley is Professor of Meta-Analysis at the School of Business at Deakin University in Melbourne, Australia. Tom has worked a lot on the development and application of meta-regression methods and the mitigation of publication bias. Tom has taught many courses in economics and statistics in Hendrix College, and currently he's the associate editor of the Journal of Economic Surveys and Research Synthesis Methods. I know Tom for quite a few years because Tom is the leader of the Meta-Analysis of Economics Research Network, and he's a member of the Deakin Lab for Meta-Analysis Research. In addition to the specific topics that this seminar will explore, we hope that the seminar will offer a brief introduction to meta-analysis and meta-regression. So without any further delay, I will give the floor to Tom. And Tom, thank you again for being here with us.
Thank you very much, George, for that wonderful introduction. This is the second time I've been treated to Professor Hortrias's generous invitations. He was also our host for our MayorNet colloquium in 2014, where we had our research seminar basically at the foot of the Acropolis. And what a beautiful place and what lovely people. It was really a great conference. And George has always been very generous. And we hope to see him again, because next year we're going to go back to Athens. In October of 2021, our research group will have its seminars in actually in Piraeus, at the University of Piraeus, which is a suburb of Athens. And it's also the gateway to all those Greek islands. So it's also a very lovely location and very convenient. Anyhow, we hope to have this conference next year, assuming that the vaccines are available. But, I was going to introduce myself, but I don't see I need to do that at all. Yes, I've been doing meta-analysis for a few years, to say the least. And we do have this research group, as George has already mentioned, MayorNet. We have a website. We hold these annual conferences. Please join us. To motivate today's talk, I want to talk a little bit about the ongoing replication crisis, which is largely in psychology, but also has fissures throughout the social sciences and business. After this brief overview of the replication crisis, I want to give you an overview of meta-analysis. And then after that, I want to focus on a few illustrations, the motherhood-wage penalty in particular. And if we have time, I'll talk about the meta-regression of the market efficiency hypothesis in finance, if we have time. I kind of doubt that we will, but whatever, it's all good. Probably most of you, I assume, have heard a little bit about this replication crisis, where psychology is having difficulty coming up with the same results, adequately replicating some of its very highly regarded experiments. They're having quite a lot of difficulty doing that. We also have a blog about this replication crisis and how we could turn this replication crisis into a credibility revolution on our MayorNet blog. Here's the website. It's mayornet.org. And there's a tab for the blogs. You can join our discussions. This is one of my favorite graphs ever because it shows so much in one diagram. This figure gives us the results from the Open Sciences collaboration back in 2015, where they attempted to replicate 100 highly regarded psychological experiments. On the horizontal axes are the original effect size as presented in the original seminal study. These are measures as correlation coefficients. On the vertical axis are the replicated effect size, also in correlation coefficients. The 45-degree line, the diagonal line, represents a replicated effect size is exactly the same as the original effect size. I mean, quickly you can see that most of the points are below the line, quite a bit below the diagonal line. And also the colors, the green represents experiments that were successfully replicated. And by that, they mean experiments that were statistically significant in the same direction as the original experiment. We could talk for hours about what's a successful replication, but that was their definition. The two big takeaway points was out of 100, only 36 were successfully replicated. And the typical effect size of the replicated experiments is only half as large as the original. There's a whole lot of research inflation, research exaggeration going on out there. There's been many of these replication efforts. I won't go into the details of all of them. They're pre-registered, multi-lab, so they're pretty darn reliable, and they're awful careful. They have much larger sample sizes. And by and large, they find the same things. I should mention that economics comes out a little bit better than psychology in these things. So what are the lessons learned from these large-scale replications? Well, essentially, as I already said, there's a lot of exaggeration, and typically effect sizes are exaggerated by a factor of 2 or even more. I mean, they get smaller when they're replicated. Thus, it's not surprising that replications are not always successful. Why does this happen? Well, there's this thing called publication bias, which is a preference for statistically significant results. Editors and authors like to report statistically significant findings. This has been long an issue in meta-analysis for decades. We have a lot of methods, a lot of discussion about this. But in particular, there was an American Economic Review article by Andrews and Casey about publication bias just last year. And since they're a Harvard MIT team, we now know publication bias must be real. In psychology, this is also called, or related things are called questionable research practices. In econometrics, economics, we think of more of this as specification searches. You keep changing your models until you get the right answers, essentially. This is sort of made famous by Ed Lemer's Let's Take the Con of Econometrics back in the 80s. However you want to talk about this, what this comes down to, there's a whole lot of researcher flexibility. Researchers have a great deal of choice on her methods, her models, her techniques, her research protocol, her outcome measures. I can go on for probably this whole hour talking about the degrees of freedom we have when we do a piece of research in the social sciences. The trouble is with all this flexibility, it leads to a very wide dispersion of the results that we see. And that's called heterogeneity. And the heterogeneity we typically see in economics and in psychology is many times, like 10 times more than what reported standard errors should suggest sampling errors should be. And we can measure these things in meta-analysis. We don't have to just speculate. What's been the responses in economics? Well, there's this transparency movement, probably most associated with Berkeley and Ted McGuell. They have their institute there. They also published a paper in the Journal of Economic Literature where they talk about lack of credibility in economics, and they're pushing for transparency. All our best journals in economics now require you to post your data and share your code. So this is kind of becoming standard. Oh, by the way, it's not part of today's discussion, but Chris Dukugliakis and I, we've done another meta study about whether or not this transparency at the journals has any effect. But I'll leave that for another seminar. Another sign of this is there's been a turn in economics more to the experiments. And, we see this evidenced by the 2019 Nobels awarded to experimentalists, but you see it other ways, and it's becoming more prevalent. And another point of this is meta-analysis has been widely recognized as part of the solution to the credibility issues to make research better. Christensen and Miguel in their Journal of Economic Literature paper, they talk about meta-analysis a lot. By the way, they're not meta-analysts, they're not part of our group, but they too see meta-analysis as part of the solution. And of course, that's what we think. We now have a relationship with Ted and his group, but we didn't before that paper. So what does meta-analysis tell us about these crises and issues of credibility? Well, we published two big meta surveys, one in economics, one in psychology. The economics one is called The Power of Bias in Economics Research. It was published in the UK's Economic Journal. The other one in psychology, What Meta-Analysis Reveals About the Replicability of Psychological Research. That was published in Psych Bulletin. Just because you guys are economists largely or finance people, let me just say a couple more words about the economic one. We collected over 64,000 estimates from 7,000 studies, roughly 7,000 studies in 159 different areas of research. And we found that the median of the median statistical power is 11.5%. Now, Cohen and convention, like the 0.05 thing, says that power should be 80%. Only 10% of economics research has adequate power. Not good. Also, maybe even more frightening is the typical economic reported result is inflated by at least a factor of 100%, factor of 2. And a third of the research literature is inflated by a factor of 4. And we know this is an underestimate. The way we calculated it, this is an underestimate. I can justify that in the Q&A or whatever. We also find that there's a heck of a lot of heterogeneity about the variation we see from study to study, result to result, is about 10 times larger than it can be justified by the reported standard errors, by the reported sampling errors. Excuse me. So what all these studies are revealing is that there's low statistical power out there, which really says the research has poor quality. There's a lot of exaggeration to the size of the reported effects, and there's a lot of differences among the reported effects, high heterogeneity. These are kind of the three problems we see in meta-analysis and in these meta-analysis, but that's also what these large replication studies have seen too. So everything is consistent. So now I turn quickly to a brief overview of meta-analysis and meta-regression analysis. George asked me to do this. I apologize. There's a lot going to happen here, and I'm going to do it quickly. I don't expect you to learn or be experts about meta-analysis in the next, 50 minutes, but I'm just hoping to whet your appetites to learn more. So here's a brief overview, a brief survey. So what the heck can meta-analysis and meta-regression analysis do? Well, they can identify and correct this research exaggeration. They can increase the statistical power by collecting all the reported results all together, and that will increase power, which is a problem. And also, meta-regression analysis is explicitly designed to explain the variation across reported results, explain this heterogeneity. Remember, these are the three problems identified, and these are the three issues that meta-analysis addresses explicitly. What the heck is meta-analysis? Well, it's a statistical analysis of a large collection of results from individual studies for the purpose of integrating the findings. This comes from Gene Glass, a psychologist. He's a guy who invented the name meta-analysis, and he's sort of the modern father of meta-analysis back in the 70s. It's an objective and systematic review of an entire scientific literature. It's widely used in medicine, health, psychology, and business for the last 40 years. And now, more recently, it's widely accepted in economics as well. And particularly in health and medicine, it's an essential part of evidence-based practice. You ever hear about evidence-based policy or evidence-based practice? It's usually based upon meta-analyses and systematic reviews, which are kind of very similar. Meta-analysis is a systematic review that just adds a statistical component to it. Well, in a nutshell, what the heck is meta-analysis? Well, essentially, It's just weighted averages, a simple weighted average. That first equation is a weighted average of effects. EI is some effect. In economics, it might be elasticity. In psychology, it might be a standardized mean difference. It might be a correlation coefficient. It could be a variance ratio. In finance, it can be any kind of thing. EI is an effect. A weighted average, you just multiply that by some weight and divide by the sum of the weights. But in meta-analysis, there's two particular specific kinds of weighted average. One's called fixed effect, the other one's called random effects. The fixed effects use optimal inverse variances as a weight. And variance is the sampling variance, which is the standard error. SE is a standard error of the reported estimate. You know, the estimate divided by its standard error is the conventional t-test. Anyhow, inverse variances are the weights, simple weighted average. Random effects is also a weighted average. It's also inverse variances. The difference is random effects allows for heterogeneity, random heterogeneity. And it measures that variance of heterogeneity by a thing called tau squared. It's very easy to estimate this if you have a meta-analysis. And so the weights now have two components. They have the SE squared component for the sampling error variance, but they also have tau squared. So the denominator there is the sum of two variances, but that's the total variance that you would expect. Standard statistical software, Stata, R, all those things, they have packages that, you know, pump out confidence intervals, statistical tests and p-values and all the rest of it. I mentioned publication bias. You know, believing is seeing is a way of thinking about this. Reviewers and editors tend to accept papers consistent with the conventional view. Researchers may treat the conventionally expected result as a model selection test, and everybody may have a preference to report statistically significant findings. I have a preference to report statistically significant findings. It's just part of the business. I'm not saying it's wrong in some sense. I'm saying when everybody's doing this, you get a distorted view of reality. You get an exaggerated view of reality. It's a selection bias is what's going on. These bullet points comes from an American Economic Review paper 25 years ago from Card and Kruger. Okay, here's a very notorious case of scientific distortion. It's kind of apropos now when we're talking about all these vaccines, by the way. In the United States, if you want to sell any kind of a medical treatment or pharmaceutical, you have to register your phase 2 and phase 3 clinical trials with the Food and Drug Administration, the FDA. It's by law. You can't sell anything in the United States unless you have safety and efficacy trials, phase 2, phase 3 trials. And these are really good experiments in theory. They're controlled, double-blind, placebo-controlled. They're considered the gold standard of evidence. And this FDA registered registry is also considered the gold standard because everything must be published, must be reported. It's not published, I apologize, must be put on the FDA registry, and that is publicly available. Okay, so for antidepressants, what we have here is 74 of these clinical trials reported to the FDA. That's the gold diamonds, 74 of them. By the way, this is called a funnel graph. I'll keep coming back to this. A funnel graph plots the effect size. In this case, the effect size is a standardized mean difference on the horizontal axis. It's measured as glasses G. You don't need to know that, but it's just a standardized effect. And of course, the bigger it is, the stronger the effect is. On the vertical axis is precision, and that's measured as 1 divided by the standard error. So the higher you go up, the larger your sample sizes are, the more precise your estimates. Without publication bias, without any distortion going on, without any selection going on, you should see an upside down funnel. It should be tightly packed at the top and it should fan out as it goes down because the standard errors are getting bigger. Sample size are getting bigger. Well, not everything that's reported to the FDA gets published. Of the 74 reported to the FDA, only 50 of these clinical trials got published. Any guesses which one? Yes, it's these blue moons or blue half moons, if you want to call them that. Of the 74, 50 of them were published. Any pattern there? I do this example because when I'm in person, I get a lot of comments about this. This is really clear that, you know, those blue moons seem to be on the right half, the larger effects, more positive for the pharmaceuticals. Hey, we have really big effects going on here. And those are the ones they allow to get published. This is bad, but it's much worse than that. If when they publish a paper in a medical journal, they report the same effect size as they reported to the FDA, then in each of these blue half moons, you should see a little bit of that gold color in the left portion of that. About half of them, you do see a little bit of that gold color there, but half you don't. And I've traced those back. And in all cases, the effect that they reported to the FDA is way over here to the left someplace. But when they get around to publish it, they find a way of making the effect even larger. I can talk to you about how they do that. Experimentalists have their tricks, just like econometricians have their tricks. But not only do they publish the bigger ones, but they find a way to exaggerate them by the time they get published. Pretty bad, I would say. Everybody agree? Another rather famous case is this minimum wage effect. On the horizontal axis, we have an employment elasticity. On the vertical, again, we have precision. This is the idea of what's the effect on employment if you raise the minimum wage. These are about 1,500, roughly 1,500 estimates, all in the United States that Chris and I collected. This is reported in dozens, and I mean that literally, of newspapers across the world, this very graph, and also the economic report of the president. A different president, I might add, but this was reported in the economic report of the president, and published in a British journal too. So, you know, everything's good. What advocates of minimum wage like so much about this graph is that all the top portion of the graph, even, you know, 2/3, 3/4 of that top part of the graph, these are the best estimates, the most precise, the most efficient estimators, probably panel estimates with humongous sizes. Maybe all of them are panel estimates. I haven't looked at that to make sure all of them are at the top are panel estimates. But anyway, all of those are very tightly packed around zero. So just a quick graphic, it says the effect zero. I mean, of course, there's a lot of other ones down at the bottom. By the way, one thing I love about funnel graphs is the crap settles to the bottom. Any value down there towards the bottom, I don't care if it's on the left or the right or anywhere, it's crap because standard errors are huge down there. And we know that those ones way far to the left or way far to the right, we know they can't possibly be the case. But anyway, the issue of publication bias, though, is there an asymmetry here? The graph should be symmetrically distributed if there's no publication bias. Now, this is not easy to see on this graph. I could focus in on it. I haven't done it here. And we could see the left half is more packed than the right half. But we don't have to make judgments about a diagram. We don't have to, you know, make these visual inspections and come up with our own opinion about them. We have statistical tests that will test these things. About 15 years ago, I came up with this meta-regression model that can detect a genuine empirical effect beyond the presence of publication bias. I call this a FAT-PET meta-regression. It's a simple one variable regression. The effect size, elasticity is the dependent variable, and the standard error of that elasticity or that effect is the independent variable. Notice the beta 0 SE term here represents publication bias. And basically the idea is that if you have a large standard error, then you're going to have to work harder, respecifying your models, searching harder in order to find an effect that's at least twice as large as a standard error. If you don't find an effect that's at least twice as large as standard error, it won't be statistically significant. On the other hand, if you have a very small standard error, probably the very first estimate you get with a small standard error will have an effect large enough to be statistically significant. So the issue is the amount of distortion, the amount of selection is going to be a function of this standard error. And actually, you can derive this mathematically from the bias you get from truncated results. And I have papers on this, but I'm not going to get into that today. In any case, this beta 0 SE term is a rough approximation for the bias, very rough. Another thing you can think about is drive that standard error, drive that thing to of SE to 0, and that bias will go to 0. And that leaves us with beta. Then the effects goes to beta. And beta now can be seen as the effect size once you correct for publication bias. And so that's my little contribution. I created a test I call the PET test, which is a test for the intercept. Both of these tests for beta 0 and for beta are just standard t-tests you get from your regression results. No big deal. But the PET test now tests whether or not there's a genuine effect beyond the reach of publication bias. I need to repeat, I haven't said it yet, but I need to repeat it several times. We always use weighted least squares. Just like the weighted averages, we use inverse variances as the weights. We know we have heteroscedasticity in this equation because the SE is right there. That's a measure of the differences in the variation. So we always use weighted least squares as 1 divided by SE squared as the weights. However, there's a problem with this. 15 years ago, I noticed that too. When we find evidence of a genuine effect, this intercept here tends to underestimate it. So what do? Well, it turns out if you use a quadratic approximation for the bias term by putting SE squared in here, we have a paper here, we have some math here, lots of simulations, lots of applications to back this up. This gives you a better corrected estimator. It typically is larger than the other intercept, and this is typically a better estimate. And we have a lot of simulations, a lot of papers. Well, we apply this quickly to the examples I just went over. Here's the antidepressants again. Take a look at the coefficient on SE. That's 1.84, and it's statistically significant. I'm putting t-values in parentheses, so 5.47 is hugely statistically significant. But the 1.84 is large. It's very large. There's a lot of distortion there in the antidepressant literature. This is just on what gets published. We're just running this regression on the 50 that gets published because except for this one example, typically we don't see into the file drawer. We don't know those 24 that weren't reported. Typically, we only see what gets published. So that's what we're doing here as well. Take a thought experiment where every antidepressant trial that's reported is statistically significant, but suppose that there is no effect. The effect is 0. In that case, we know the coefficient on standard error will be a little bit bigger than 2. It's not quite 2 now, but it's not that much smaller than 2. It just, the fact that it's so large, saying there's a whole lot of distortion to the right here, pushing those, but we know that already. In this case, we know that already. It's just nice that this statistical model confirms that. Once we allow for, take that publication bias and put it to the side, take a look at the intercept. The intercept is 0.13, and it's statistically significant, 2.5. When that's statistically significant, we should run the other second regression equation with SE squared. When we do that, the intercept, that's called the piece, becomes 0.29. And by the way, 0.29 relates to the average effect is 0.47, which is, it's about a third reduction in that effect size. And here again, we know what's in the file drawer. We know it's at the FDA registry. If you take a weighted average of all 74 of those, it turns out the effect size is about 0.28. So the statistical correction does a really good job of seeing into that, what's usually invisible file drawer. And we know that that's the case here. Take a look at this model for the minimum wage results. Again, look at the coefficient on SE, a minus 1.6, a negative 1.6. It says the distortion is pushing things to the left. Oh, I didn't mention, of course, we should expect an adverse relationship between wages and employment, because this is the law of demand. It's a core part of neoclassical economic theory. You raise a price, you expect the quantity of demand to go down, so you expect this inverse relationship. So we'd expect if there's any bias, it's a bias towards that. And of course, it's statistically significant. T-value is 4.49. But what's really important here is once we put that potential bias to the side, what's left over is nothing. The elasticity is a minus 0.01. That's practically, from a policy standpoint, is trivial. It's negligible. By the way, this result, I won't show it today. This result is very robust. When you do a big multiple meta-regression, you look at various subsets and you use different methods for your meta-regression. No matter what you do, you always come up with the result that the size of the employment effect is so small that it's immaterial. And not only we get that result, there's been at least 4 independent replications of these meta-analyses on a minimum wage. And everybody gets the same result, and they're not related to us. They're independent. It's a nice thing about meta-analysis. It is itself replicable, and our work is often replicated. Almost, I think probably just about all of them have been replicated. I think that's enough to say. So what does this correcting publication bias thing do? Well, again, we've had lots of applications, lots of simulation studies. But another piece of evidence came from psychologists and economics, kind of a combination of that group. People we didn't know, Carnarvon et al. They published a paper in Nature last December, less than a year ago. And what they did was they did a systematic review of all these large psychology replications that could be linked to an associated meta-analysis. So you had to be on the same experiment. The replication and the meta-analysis. So you're talking about the same thing. They found 15 pairs that could be linked like this. And about half of those experiments were successfully replicated and half weren't. 7 versus 8, I remember. Random effects, RE, was very biased, and it had a 100% false positive rate. It was always statistically significant whether or not the effect could be replicated or not. Also, other methods to do publication bias, a thing I haven't mentioned, trim and fill. There's these other things called selection models. There's different flavors of them. One flavor is the flavor that was published by Andrews and Casey in the American Economic Review. They were also employed here, and they were found to be quite biased, and they had high rates of false positive. One exception, wasn't our paper. One exception was FAT-PET-PEESE. It had almost no bias, and it had a 1 out of 7 false positives. So it had a low rate of false positive, at least comparatively. We also have some bias resistance methods, publication bias resistant weighted averages. Experimental scientists just stop at weighted averages. Econometricians, we do meta-regression. But if you want to have a weighted average that's not so biased, we suggest this unrestricted weighted least squares. It has the same weights as fixed effects, inverse variances, but it automatically corrects for heterogeneity if the heterogeneity is there. So it's like random effects in that way. But simulations and application shows it's less biased than random effects if there is publication bias, and it's better than fixed effects if there's heterogeneity, because it automatically accounts for heterogeneity. It's even a simpler regression. It's just a t-value versus the precision, which is 1 over standard error. T-value dependent variable, precision, 1 over standard error. The independent variable, this is weighted least squares, by the way, and there's no intercept in this model. And just the confidence interval, standard errors, p-values you get from the simple regression without an intercept will be the unrestricted weighted least squares. And again, simulations, applications all show, published papers all show this works pretty well. And we've even improved on this by just running that same unrestricted weighted least squares just on the top part of the funnel, just the part of the funnel where we know statistical power is at least 80% or higher. And by Cohen's convention, 80% or higher, that's considered adequately powered. That's what medical research, that's how they figure out their sample size. They try to get 80% power. We call this the WAP. One of the things I love about WAP is it focuses the reviewer's attention, the meta-analysis analysts, attention on this critical dimension of statistical power. I think that's power is really important, and it's often ignored in research. We published a couple of papers about this, and in a nutshell, much too quickly, I understand. That's an overview of meta-analysis. I know that was too fast and furious, and I know you couldn't possibly get all that. So I'm going to slow down a little bit and go over some examples. The first example is this motherhood-wage penalty, also the child penalty, baby penalty. My colleague and former student, Megan DeLynn Leonard, and I published this recently, The Wages of Mother's Labor, kind of a pun there. So why should there be this penalty for mothers? Why should having a baby cause workers to have lower wages? Well, of course, it's not fair, but what's the economic explanations? Well, I mean, some mothers will take time out of the workforce to raise the children, and so they'll have that lost work experience, and they'll have the lost acquisitions of new skills because they're not in a labor force, or at least not in the labor force for the whole time. Compensating differentials is an explanation. That's the idea that mothers have different job amenities, different job dimensions they look for, things like part-time work, family-friendly work, work where they can have more flexible hours, work where they don't have to travel so much. And maybe mothers are willing to pay for those amenities by having a lower wage. By the way, Megan, she's a mother of 4. She fits this category, this explanation. Maybe mothers are less productive. I mean, they spend more time at home, maybe. And so maybe they spend fewer hours or not as intense hours doing market work. That's a possible explanation anyhow. Maybe it's just discrimination on the part of the employers. They think mothers are not committed, or they don't work as hard, or whatever. Maybe it's just discrimination, or maybe it's sample selection. We know that women with lower skills and lower pay have a lower opportunity cost of taking time out of work. So they have a smaller opportunity cost for having children in some sense. So maybe there's reverse causation going on here, or selection bias. It's a possibility. That's all I'm saying. We did an exhaustive search on Google Scholar and other platforms of any kind of a keyword that's associated. I mean, we even use things like wage penalty, family gap, on and on. But we also concatenated these with things like baby and child and motherhood, and a lot more combinations than what you see here. I mean, it's really easy to do these searches now. When we got a hit, we found a paper which actually had some estimates in it that we were looking for. We looked at its references, we looked at its bibliography, and we traced down all the papers it cited. And also we went the other direction. We identified a few seminal papers, and we looked at all the papers that would cite one of these seminal papers. And we came up with a list of 142 papers, but not all of them had results. Not all of them had empirical estimates. Only 49 did, but we had almost 1,900 estimates here of the child penalty, the baby penalty. We also, for every one of these, think of this as 1,895 rows, we had 40 columns. We had the estimate and 39 other factors that might affect the size of the reported estimate. 39 factors we coded for. The main reason the paper didn't make this cut was if they were a policy paper or a theoretical paper and just had no empirical estimates. That's typical, by the way. That's what most papers are. They're not empirical. And even some of the empirical ones had no standard errors or no way of calculating a standard error. Some of them ran separate regressions for women with children and women without children. And there's no simple way of getting a single estimate there or the standard error, unless we had all the variance covariance matrices, and that's not reported. Or some of them did this as an interaction term, and it's not exactly the same dimension. Because you guys are in London, I should mention something about UK mothers. We had 5 studies about UK mothers and 112 estimates. And the average motherhood wage penalty was 12%, 12%. And that's among the highest of all the countries. Now, that's just the overall average. That's not corrected for all the factors, and we're going to come to that. Here's just a bar chart, just a frequency distribution of these 1,895 estimates. You see most of them are compacted between 0 and 0.05, negative 0.05. So that means there's between a 0 and a 5% penalty. Negative means penalty. And the next highest bar, about 17, 18%, is between 5 and 10%. Most of them are packed up there, but they're spread out. There's even quite a few, I mean, in terms of numbers, there's quite a few positive estimates even. The funnel graph looks similar, all it's different. Instead of frequency, we're graphing here the precision of the estimates. And I'm pretty sure these top ones come from large panel studies. Those will have the most precise estimates. And notice how the top half or so of the funnel graph are all packed, not around 0, but between 0 and minus 0.1, minus 10%, 10% penalty, which, you know, is awful consistent with what the bar charts are showing too. They don't have to be exactly the same. You could have a hole in the funnel, but we don't. Okay, I should come back to that again. I hit it a little bit too quickly. So about publication bias, is there a distortion? Is this graph symmetric, or is there a distortion to one side or the other? Again, you don't have to answer that question. Our statistics will answer that question for you. Again, looking at descriptive statistics, the average penalty among these 1,895 estimates is about 5%. Now we do the random effects, weighted average is a little bit smaller. It's about 4%. When we do fixed effects and the unrestricted weighted least squares, they give you the same point estimates. If you notice, they have different confidence intervals, different z-values though, different standard errors. They're just under 3%. And the WAP, which just looks at the top part, that's just a tiny bit, virtually the same, 2.7% is the average wage penalty. Oh, by the way, there's also a heck of a lot of heterogeneity here. The variation from one estimate to the other estimate is 20 times larger than what you could account for from the sampling error. Oh, just to remind you, you get the unrestricted weighted least squares by this simple regression with just one independent variable and no constant. Again, when you use these methods to account for publication bias, the effects shrinks in half. That's what we saw for economics as a whole. It turns out that's what we see in this particular case as well. Again, take a look at the coefficient on SE. We find a -1. Chris and I have published a paper suggesting anytime the absolute value of that coefficient is 1 or larger, publication bias is substantial, or at least it's consistent with substantial publication bias. There's a substantial amount of asymmetry, be a more precise way of saying it. It's also statistically significant, and of course it's in a negative direction, which is what we expect. We expect there to be a penalty. And so there seems to be some selection for statistically significant penalties. Once we set that to a side, we find that the intercept is now weighed down to 0.024, but it's statistically significant. And when that happens, you should use the PEESE estimate, which replaces SE with SE squared. And then the intercept goes up to 0.028. And so that's our overall estimate of the size of the child penalty. And notice 0.028 is exactly what unrestricted weighted least squares get. And for all practical purposes, it's what WAP gets. So our three preferred estimates are all giving us, for all practical purposes, the same thing. And by the way, everything is highly statistically significant. Even though these are small estimates, in terms of their t values or their z values, they're very statistically significant. That's not the issue. There's always a problem in observational economics and econometrics. Really, the results we get are conditional. They depend upon, what country we have, the culture of that country, its laws, what kind of markets are there, the legal system, the history of that country. I can go on and on. It also depends upon how researchers study this effect. The models, the methods, the type of data, the type of experiments, all these things can influence the size of the effect you get. So I'm not sure it really makes any sense in econometrics to use any one number, no matter how good the number is, to represent an entire economic research literature. So that's where meta-regression comes in. We need to explain this wide variation, and we need to explain and understand its richness. And we're going to use what I show here as Z variables. I guess you would say Z variables. What I did is I took equation 1 and I just blew it up by adding a bunch more variables. The Z variables allow for any kind of heterogeneity, and we're going to put 39 different factors. Maybe it's 38. I think SE is one of the 39. We're going to put 39 or 38 of those factors in there to allow for heterogeneity. If we wanted to, we could also blow up the publication bias term, which is the SE term, and we could multiply it by any number of factors and allow for differential publication bias. This is a lot of variables, but we have almost 1,900 observations. So we have plenty of degrees of freedom. And again, just to repeat myself, all of these things, meta-regression, we do weighted least squares with 1 over the standard error squared as weights. I'm not going to go over this because of time, but we coded these 39 factors. There's some of them. There's some more of these factors. Many of them have to do with potential misspecification bias by what variables you included in your regression, what the original study included in its regression. And anyway, here's all the factors. We put all 39 of those into our equation, and we did general to specific with weighted least squares. That is, we took out the variable which had the highest p-values one at a time until we ended up with just statistically significant results. We had 23 of these factors were statistically significant. I don't really care about that, but we just want to see what the robust results are, the factors that's important, no matter how you study them, no matter what model you use, what factors always jump off the page. That's the only thing we talk about. That's the only thing we think is really real in our meta-regressions. Column 2 are cluster robust because we have multiple estimates per study. So those might be dependent. They might be related to one another. So we need to adjust the standard errors for that potential dependencies. Cluster robust is one way of doing that. Column 2 has the same coefficients as column 1, but different standard errors. And so the t-values in parentheses, always t-values I'm using, are different. Column 3 is fixed effects panel models. And I think those are the best because panel models allow for unobserved differences in qualities across the studies. So there could be things going on about the studies we don't observe, but the fixed effects panel actually accounts for those. So that it's a stronger design for meta-regression, I would argue. Anyway, so we did that too on the same set of variables. And a few things to look at. You see SE is always statistically significant and negative. That's a publication bias thing. The US dummy variable, that's US compared to all other countries. Its value is about -4, -5, which says women in the United States have a larger penalty than the average country, than women in the average country, mothers in the average country. Selection correction is generally statistically significant, and it's about 1%. So if you correct for selection, you actually get a larger penalty. More negative means larger penalty. So this dismisses the selection argument because actually controlling for selection makes the penalty larger. It doesn't go away once you correct for selection. If anything, it gets bigger. Actual experience is important. That's pretty obvious, but that's important. Time out, time that women spend out, mothers spend out of the workforce, that makes the penalty about 1 to 2% smaller. But even after you make allowance for that time out, there's still a child penalty in addition to that, on top of that, at least for some countries. Well, here we have this complicated meta-regression model. So what's our estimate now? Well, there isn't any single estimate. It depends upon all these independent variables. So now, if we want to use this meta-regression model to come up with an overall assessment of what the size of the penalty is, we have to make some choices at the values of the independent variable. You can look at this as a benchmark study. We try to think of it as best practice. We try to use what's probably the better models and the better methods. We try to plug in those values. There's some debate about that, and we can talk about that in discussion, but we need to have some values to plug in there, and we try to use best practice. I think best practice would be the studies that use panel models originally and had fixed effects, because those control for unobserved worker productivity, and productivity could be important. Also unobserved worker ability. Those models automatically correct for that. That's a stronger design. We also think you should not omit any important variable. If you do, you have misspecification biases. We should drive SE to 0. That gets rid of publication bias, and so on and so forth. You should control for selection. We looked at data in the 2000. That's arbitrary, but we wanted to look at more modern estimates of the baby penalty rather than ones back in the 1970s. That's an arbitrary selection choice. Now, when you do this for the average country, just for the average country in the world, the size of the baby penalty, the child penalty, virtually is nothing. It's just like minimum wage. It's so small as to be irrelevant. But that's not true for all countries. And here's a list of those countries that are statistically significantly different than the overall average across all countries. And the U.S. has a larger penalty. The penalty for U.S. mothers is about 4%, and that's after you correct for publication bias and you use the best estimates and all those kinds of things. United Kingdom is much worse. The penalty in your country is twice as bad for mothers, 8%. By the way, this is per child. So a mother of 3 in the United Kingdom should expect her wages to be about 25% less than they would be if she didn't have any children. Germany, we're still about 10%, and Norway is the worst one. While it's statistically significant, it has a huge confidence interval. This is only based upon 2 studies. I don't really trust the Norway estimate. I think further study needs to be done on Norway. But that's the results we got. So what does this explain? Does this explain our hypotheses? What is this meta-regression tells us? Well, we said something about lower productivity. We don't think that that's the explanation, because we don't have any direct measures of productivity, but the indirect ones like marriage status, divorce status, didn't have any effect on the child penalty. Also, the fixed effects panel, which controls for unobserved productivity, we're using those. And even after we use those, we still find a residual child penalty, at least for those countries. Is it lost work experience? Well, we saw timeout had some effect, but there's still a penalty above and beyond what you would attribute to lost experience, however you measure that. Compensating wage differentials, no. Factors like occupation, part-time status, government work sometimes are thought to be more family-friendly. Those factors did not influence child penalty. Sample selection, no, it actually goes in the wrong direction. And even the 1% is still too small to explain it all away. So no, it's not sample selection. So basically we're left with discrimination, or simply a belief by employers that somehow mothers are less productive. That's the primary explanation we have that's left over. Thank you.
Oh, almost perfect timing, Tom. 5 minutes earlier. Excellent. And I see that we have some questions.
I have another example of efficient markets, but I didn't think I would get to it, so don't worry about it. I'd rather handle the questions.
Okay, and by the way, since you finished your presentation, I would like to say to our attendees that we have about 15 minutes for Q&As. However, we will post a Zoom meeting link in case that any of the attendees want to talk privately, to have a chat with Tom, with the presenter. At least myself and George Capodanios will have the opportunity to have a chat through this link with Tom, If anybody else wants to join us, please feel free to join the link. At some point, you will see at the chat the link posted. So yeah, here it is. Here it is. So we have a question. Elisa asks, when do you start considering a sample size of independent studies too small to conduct meta-analysis?
That's a great question, and it does not have a good answer. It's not my fault, but there's not a really good answer for that. Personally, I would probably use an arbitrary rule of 10. I know it's arbitrary, but I've done a lot of simulations, and it just gets silly at some point. Medical researchers that do these fancy clinical trials, the average meta-analysis in medical and health fields is less than 5, the average. And there's a big push to do a meta-analysis early in those fields because you want to get it published, and you get a good meta-analyses usually give you good publications. And so they'll publish a meta-analysis with 2 or 3. To me, that's ridiculous because I can keep 2 or 3 or 4 ideas in my head at the same time. I don't need to come up with a summary of them. But there you go. These publication bias methods, which I'm actually creating new ones. I mean, their power goes down, and their power gets less than 50% if you go below 10. But 10 is totally arbitrary as well.
Tom, I may have a relevant question. Let's say that you want to conduct a meta-analysis with 100 regressions or 1,000 regressions. Now, let's consider 2 possibilities. The 1,000 regressions may be the outcome of a few papers with many regressions or many papers with few regressions. Does it make any difference? Is there any kind of rule of thumb? What's optimal? What's preferable? Well,
to me, you're looking at it backwards. No offense there, because first you look at a topic, you want to have a better understanding of it. So the first thing you do in meta-analysis, I want to study some hypothesis. I want to study some phenomenon. So the research is the research. You can't choose. And what meta-analysts do, they do a systematic review. So it's important to include all relevant results. So you're not committing selection. Now, there would be a difference in power from what you're saying, but I wouldn't, I haven't actually run that particular simulation study. I have seen some similar, but I'm still not worried about that, George, because I'm going to use fixed effects panel. So if there's a bunch of estimates per study, I'm going to account for that. And I'm going to model that. I mean, that's bang. In fact, I know that's the end point, and I know that's the results I'm going to have the most faith in. So I guess, if you only had a few studies, then that also suggests that it's not going to be as powerful because, you don't have as many degrees of freedom for that panel. Does that answer your question? I don't know.
Yep. Well, I had a prior, but I just wanted to get your view on it. Do we have other questions?
George, I have a quick question.
Yes, I think that Tom can hear you directly, right?
Yes.
I can.
Hear me? Yeah, hi, it's Jack. Yeah. So a lot of your examples, thanks for the talk, by the way. A lot of the examples you gave was sort of seem to be using cross-section or panels or short panels, I guess. My question was really, if we're interested in sort of macroeconomic relationships where you use time series data, for example, where you typically expect sort of relationships to really be drifting around over time. So you expect like your true effect maybe to change over time. Can meta-analysis sort of say anything about that? Because if I think about your graph of like the effect size versus the precision, you might expect your effect size to be all over the place just because actually relationships are genuinely changing over time.
Yes. One of the criticisms, an apt criticisms, particularly for econometrics you can make for this talk is maybe I shouldn't talk about any overall estimate. Maybe I shouldn't even put up a funnel graph, because that implicitly says that there's some underlying mean. And in econometrics, everything is so conditional. We know we're going to have a boatload of heterogeneity. And whether that's over time, by the way, the over time, we do this all the frequently. We can put time variables, and we do. We put trend variables as one of our moderator variables, or anything else too. And whether or not the series is co-integrated or not, and so on. You can code for all those things that you think might change some of these time series. The minimum wage was cross-section and time series. There were some time series estimates. So we actually have a variable that codes for what kind of data was used. And is there a difference between the time series estimates versus cross-sectional estimates versus panel estimates? We use those as moderator variables. I think I still like looking at the funnel graphs personally, even though I don't take them all that seriously. They give me the idea of the distribution. And what we want to do in our meta-regression, we want to explain those differences. I actually use funnel graphs if there's one observation or a few observations that doesn't seem to be part of the body, one side or the other, then I'm saying there's some really important heterogeneity, and I better well have a variable to explain that. If I don't, I'm really missing the boat. Does that answer the question?
Thank you. Yeah, thanks.
George wants to ask a question.
Yes, can you hear me?
Yes.
Yeah, great. Thank you very much, Tom, for the presentation. I'd like to ask you to talk a little bit more about how you determine this quantity tau, which comes about in your weights at the beginning of your slide. It felt like this is the one where it is a bit more vague. So maybe you can talk a little bit about that.
Very vague. I mean, so I 15 minutes, I try to go over all the meta-analysis. I apologize for that. You're of course right. That comes automatically out of what's called a random effects model. And the random effects model assumes that there is no single true effect, that there's a mean effect and then there's a distribution of true effects. And they assume that the distribution of true effects is normal with this unknown variance. But we have all these estimates and we have all their standard errors. And I hesitate to say it's an easy calculation. It is kind of an easy calculation. It's just a formula. That takes that variance that you see and basically factors out the observed sampling variance, which comes from SE squared. And then the variance that's remaining, the variation that's remaining, you can use that to estimate tau squared. The thing that the estimator that's common is called the de Simeon-Laird estimate, and it's a very awkward formula, but it's just a formula. It's a standard output that you'll see in any of these packages that do meta-analysis. There's also 14 different estimators. There's maximum likelihood estimator, restricted maximum likelihood estimators for it. I mean, there's more sophisticated estimators, but I don't know if that answers your question. I mean, I don't have the formulas in front of me. They're on my simulations, of course. But most meta-analysis just ignore these things and they just hit the buttons, of course, and those things are automatically calculated.
Thank you very much. Thank you.
Sorry, I did have one more actually.
Yeah, I have one more, but please, Jack, go ahead.
Just as like a kind of bigger picture question. So I remember when you mentioned how you found your sample of different studies, you mentioned that for quite a lot of them, you couldn't even find standard errors reported, which seems obviously like a huge problem for meta-analysis studies. I wonder if you could comment on, actually how common you find that is. And also, do you think there should be more onus done kind of in academia in general to sort of, force, inverted commas, people to make their studies much more replicable and useful in terms of being able to use them in meta-analysis by presenting standard errors and other statistics on their results?
This is an old problem. I've heard discussions of this for 20, 30 years, not just in meta-analysis, but just researchers. My wife's in education and also psychology. So I kind of hear, these people don't even report anything, and that's terrible. And obviously you're 100% right. It's getting less and less frequent, but we always find some people. Well, we're looking at the whole literature back to the 1970s, or whatever, as far back as we can go, and some of this tends to be, the 1970s thing. I don't know. They just reported the slope and intercept coefficient or something. And if we have the p-value, if we have the t-statistic, we can back in to the standard error. Well, if we have any two of those things, we can calculate the other, and we do that. So we always find that this does happen. But I haven't done a systematic study of that, but I'm pretty sure it's happening less and less frequently, and probably pretty darn rarely now in econometrics. Now with transparency, you got to show everything. And now with transparency, heck, the meta-analyst could grab the data and we could do the calculations ourselves. That wasn't so easy, back in the day, or going back to the 1975 paper, we're not going to be able to do that. It's more of a problem in some of these other fields, I would say.
Thanks.
I don't think we have to do anything special about that now. I think transparency will cover it. Yes, George.
So is it? Now, I think that we have another couple of minutes left, and just to remind the attendees that we can join Tom for an informal chat in the Zoom meeting. And just to close this nice discussion and this nice presentation, maybe I can ask a broad question about meta-analysis. The first paper I did myself on meta-analysis was, what I had in mind was that meta-analysis is a quantitative literature review. Honestly, the first time I came, I had an invitation from a small journal to write a paper on Taylor rules. And everything at the moment was written. And I said, they asked me for a literature review. I said, I can try to make a quantitative literature review. But clearly, meta-analysis is something more than a quantitative literature review, right?
In my Journal of Economic Perspectives paper, that's what I called it. I think it is a quantitative literature review. I do think it's that. Of course, it's not necessarily a simple or descriptive one. You can use, and we do use, all the econometric tools that you use in econometrics. You can use that whole panoply of tools to do a meta-analysis or meta-regression analysis. So I do see it as a quantitative literature review, but it can be a pretty darn sophisticated one.